All right, good morning, everybody. It's a great pleasure to have this opportunity to teach this mini course on contraction theory. It is September the 13th, 2023, and it's my pleasure. I'm at the University of Linkoping, Sweden, invited by Professor Claudio Altafini. All right, so there is about 10.5 hours worth of lectures that I will deliver, covering 3 broad sets of topics, fundamentally. The basic theory of contracting dynamical systems in discrete and continuous time, mostly focusing on vector spaces with arbitrary norms. I'll make sense of this in a few minutes. And then I will endeavor to show you as many examples as I can of systems that have this property, and therefore having the basic contractivity property also carries with it a number of consequences. So we will see that as well. And finally, the main contractivity property is a strong property. It's a lot to ask of your dynamical system. And so then we will look at a number of extensions and variations on the theme and weakenings of the main basic definition. And that's not quite a contracting dynamical system. Maybe it's weakly contracting, maybe it's semi-contracting, and we will go from there. All right. So what is the contractivity property? Well, contraction theory is a notion, is a theory of stability with 2 properties. It is robust, so it automatically comes with a number of robustness properties, which we will see. It can handle, well, I have a list there. I'll mention that in a second. And it is computationally friendly, meaning to say that it lends it. So if I have a continuous time dynamical system and I wish to discretize it in time, there are clear guidelines on how to do that. If I have a disturbance and I can upper bound the disturbance, then I get automatically explicit upper bounds on the error in the states, and so on and so forth. So everything can be quantified. So for those of you who may remember the basic definitions of stability theory, the definitions start with something like, for all epsilon, there exists a delta. Or there are other definitions that go along the lines of, there exists a class K function, a class KL functions. So those epsilon delta and class K, KL functions tend to be anonymous, tend to be quantities that you do not really know. Whereas in contraction theory, I will be using Lipschitz constants and one-sided Lipschitz constants. And these will be numbers. This will be scalar numbers. And therefore, everything will be very explicit. Contraction theory is the union of 3 theories, essentially. It's fixed point theory, stability theory, and the geometry of metric spaces. So what do I mean by this? So the original work by Banach in 1922 was the Banach contraction theorem. I hope you guys know it. I will review it in a few minutes. The main point of it is to compute, to ensure the existence and give you an algorithm to compute a fixed point. So the Banach contraction theorem is one of the most famous, widespreadly an important result in analysis, in calculus. So it allows you to, it's almost like the standard tool to use when you're looking at partial differential equations and all sorts of implicit function theorem, the inverse function theorem, and so on and so forth. And so there are books entitled Fixed Point Theory. There's a sequence of books. There's a field in mathematics, and it has contraction theory at its core. At the same time, if you look at the definition of the theorem and the way the Banach contraction theorem is proved, what it is, it's a sequence of points that come together. It's actually a theorem about dynamical systems, because it really just talks about 2 sequences that have to come together. So we'll look at the proof in a few minutes. So it's a dynamical system theory. So it's a perfect match. Contracting dynamical systems automatically have Lyapunov functions, which we will see. And then the last comment I have regarding metric spaces is the following. In general, this idea of contraction works not only on vector spaces with norms. So Rn with a 2 norm is the easiest case, but it works on arbitrary spaces that have notions of distances. So maybe you're working on the circle, your problem has to do with points on a sphere, and you can define a notion of distance between 2 points on the sphere. Maybe you're working with orientation of a satellite. You can certainly define a distance between orientation matrices. Maybe you are working with positive definite matrices because you're writing some kind of a Kalman filter, or you're estimating covariances, positive. Well, there are metrics on the space of positive definite matrices. And when you write an algorithm, perhaps you wish to be able to show that that algorithm is a contraction. And if you do that, then you have many great properties, which I will show. All right, so here, maybe it's not necessary if I go through every single one of these property one by one. Right now, we will see them. We will see them together. But just to quickly give you an idea, if you satisfy the strong contractivity property, then there exists a unique global exponentially stable equilibrium. It comes with at least 2 Lyapunov functions, and your system enjoys a number of robustness properties: bounded input, bounded output, finite input state gain, robustness with respect to unmodeled dynamics, robustness with respect to delayed signals and dynamics. If you inject a periodic input, you obtain a periodic output. For example, I know of very few, if no other theory, that allows you to consider the following problem. Imagine you have an animal in water, and imagine that the central pattern generators in the neuronal system are generating a periodic signal. Why is it true that the animal is moving in a periodic way? So you have a periodic forcing and non-linear system. Why is it true that the periodic input generates a periodic evolution with the same frequency, with the same period? Well, contraction theory gives you that immediately for free. We will talk about interconnection properties. So when is it true that interconnecting contracting systems gives you a contracting system? And as I was briefly hinting at earlier, actually this theory the theory focused on dynamical system and specifically on ordinary differential equation. That is to say, continuous time dynamical system. It all started with the interest of designing accurate numerical integration schemes. When do numerical integration scheme reproduce faithfully the evolution of the continuous time dynamical system? And it turns out the answer is when the dynamics is contracting, or in any case, the one-sided Lipschitz constant, which is the measure of the expansion in the divergence of solutions, that quantity is bound. And we will use that for machine learning purposes, as we will be talking about equilibrium point computation. So the upshot of this discussion is that I believe it is useful and valuable to be informed about this theory. You can use it to search for contraction properties. Sometimes people hand you a dynamical system and maybe it is contracting, and if it has that property, it's really good to find it. Sometimes it is useful to design engineering systems so that they are contracted. Maybe you design a receding horizon model predictive controller. Well, you would like to understand the conditions under which that closed loop system is contracting, because then, well, it will have those properties, right? And in terms of verification, if you want to be able to ensure that the compositions of things, maybe hybrid systems, well, then again, I believe this theory can be helpful in that context. All right, just a quick mention that I get the privilege of giving this talk to you, but really everything I present is well, first of all, there's a lot of historical work, right, over the last, since 1958 and even earlier. 1958 is the work by Dahlquist and Lozinski. 1922 is the PhD thesis work by Stefan Banach. But okay, since then, the specific results that I have obtained have all been in collaborations with my PhD students, postdocs, and faculty colleagues that I wish to thank. Now, all right, so here's an outline. I will maybe talk a little bit about history and resources first. I will then talk about the main contractivity property. I will then show you examples. I think the examples are very important. If you have a theory that doesn't have example, it's not a very valuable theory, right? The more example, I'm always looking for new examples. And then after that, after I have motivated the theory with some examples, I'm going to talk about the properties of contracting dynamics. So that list of properties in that slide number 2, they're going to come in here. And then after that, I will go back to some examples and show you some applications. So I'll have the examples, but I will try to do something useful with the examples. And then here's the point that I was making, that it is not true that all systems live on a vector space with a norm, finite dimensional, and that they are strongly contracting. They may be weakly contracting, also said to be non-expansive. They may be semi-contracting in some sense. They may be locally contracting. They may be contracting with respect to a Riemannian metric on a manifold. So these are generalizations of the main property. And then I don't believe I'll have time, but there's just a lot of extensions and other things that come to mind. Okay. I think I mentioned this already. Stefan Banach wrote his PhD thesis between 1918 and 1922. He was a self-taught mathematician. So another mathematician, an established mathematician, whose last name I never remember, Steinhaus, met him in a park. And Banach was talking mathematics with a friend of his. And so in Warsaw, you can find this beautiful statue that immortalizes that moment when the self-taught Banach was met and was discovered. And a couple of years later, he published his PhD thesis, which contains the theorem that inspires this whole theory. I mentioned that in 1958, Gerhard Dahlquist, at the same time, Sergei Lodzinsky in Russia wrote a paper that has many of the same concepts. The first control person to use it was Charlie, to the best of my knowledge, was Charlie Desor in 1972. And this paper is really very interesting because it talks about control, it talks about computation, it talks about proving convergence of Euler and Newton-Raphson computational methods. So it's really hinting at this concept that contraction theory has both stability and computation. And then finally, that's the paper by Jean-Jacques Slotin that I mentioned. Beside the students and colleagues, lots of control scientists have worked on these topics. This is a very incomplete list of scientists who influenced me, and I have read as much as I could, but there are works for sure that I have forgotten. Now, beside my personal take on the subject, there are also a few surveys that have come out relatively recently. Eduardo Sontag and Zara, actually I should say Zara Aminzareh, in her PhD thesis, collaborating with her PhD advisor Eduardo Sontag, wrote a wonderful survey for CDC 2014. And then Mario Di Bernardo with his group, including Giovanni Russo, wrote a very nice book chapter in 2016. Jean-Jacques Slotin with Hiroyasu Tsukamoto and Sonju Chung wrote a survey in 2011. And one of the things that I have not yet had a chance to study, and therefore I will be unable to present to you, is a numerical analysis approach. How do I compute Riemannian metrics with respect to which my system is contracting? For that, I would like to point you to the work by Peter Giesel, Hafstein, and Kawan. This is a wonderful survey. So that's also very recent, and that's telling you that there is quite an interest in developing numerical methods to search for this contractivity property that I am talking about. All right, here's a picture of Stefan Banach. His career was on an explosive trajectory. As soon as he was discovered, in just a few years, he became full professor, member of the Polish Academy. He was the founder of the School of Mathematics, the first functional analysis book, and then it all came to a crashing halt during the Second World War. It turns out that, since I'm Italian and I taught this course in Napoli last year, that 10 years later, but independently, Renato Caciopoli developed a very similar theorem. In fact, some people even argue that 50 years earlier, Picard himself in his Picard iteration was really talking about very similar concepts. And okay, so this is a little history of Renato Caciopoli, who also was not did not have a great time during the Second World War. All right, so now here's another. We're still talking about history and resources. The literature in the last 50 years has studied extensively this property, however, with different names. So this list you see is a list of articles in which people studied properties and gave different names to the same identical property. And so I will stick with the language once that the Lipschitz maps, but you should know that, for example, Chua was calling this uniformly decreasing. Filipov in his work on non-smooth analysis didn't even give it a name. Other people invented names like non-negative measures, dissipative Lipschitz maps, log Lipschitz constant. Gustav Söderlind uses that in his work. Quad maps, incrementally quadratically stable systems. So one of the problems that has led me to do a lot of archaeology work in studying all this literature is that the nomenclature is not widely established and agreed upon. So that is a problem. And these are contractivity conditions that do not involve taking derivatives of the vector field. And then there is a whole list of other works going back to the original work by Davidovich and Krasowski and many others that instead work with the Jacobian of the vector field. And also these conditions have been given all sorts of different names over the years. So as you consider doing your research, you have to be a little bit paranoid that you're studying a subject, you think about the problem in a certain way, there's a natural name for it, and yet maybe it has been studied by others with other names, right? And that's certainly what happened in this discipline. If you download the slides, there has been a workshop, recently a tutorial session, tutorial papers, various presentations. These lectures hopefully will be on YouTube and textbook. So there's a lot of resources by now that you can find. This is the textbook. And these are selected references from my group. All right. Okay, I'm done with the history and the resources. And now I would like to start with the actual content of the course. Let us start with the main result, which, as I was telling you, generates the whole field. And that is the celebrated Banach contraction theorem. So you have to have a complete metric space. So it's just a space, it's a set of points. There's a notion of distance between them. That's why it's a metric space. The distance between points has to be non-negative, symmetric, the triangle inequality. And the space has to be complete, which I don't want to review the definition because in our cases, it will always be complete. But it has to do with Cauchy sequences having a converging point. So if you end up having to deal with in your research and in your work with unusual spaces, then you can go back and look at the careful definition of a metric space and its completeness. Then you have a map. This map is a self map from the space to itself, and because you have a notion of distance, you can certainly look at the distance between t of x and t of y, where x and y are two arbitrary points in the space x, and you hope that this is less than equal than L times the distance between x and y. So if your map T satisfies this property, it's said to be Lipschitz, Lipschitz continuous, with Lipschitz constant L, lowercase l, which is non-negative. These are all distances, right? You need this bound to hold for all L. Now, if that Lipschitz constant L is greater than 1, then you need another theory. Because, I'm sorry, I'm trying to be silly here. So the Lipschitz map is called a contraction mapping, or just a contraction, I'll call it. if the Lipschitz constant is strictly less than 1. So then, if you have 2 points and you apply the map, the distance between the two, well, if you repeatedly apply the map, the 2 points become 2 trajectories, and these 2 trajectories are coming together because the distance between them is decreasing by a factor L. So L becomes the contraction factor. Now, the theorem tells you that the theorem has multiple consequences. Tells you that your map has a fixed point and it is unique. So this is an existence and uniqueness result. My light blue does not quite show. That's okay. We are in luck. I have a darker blue. There. So in some engineering problems, maybe you're interested in stability of your dynamical system, but maybe you're actually interested in knowing that a solution exists. So, for example, in gains, you're really interested in knowing if a Nash equilibrium exists. In power system, you're really interested in knowing if an operating condition exists. So if the amount of injected power and power consumed by the customers, can I find a profile of energy transmission? So just finding an equilibrium sometimes in itself, it's a very important problem, right? In optimization, you want to find it. So this existence and uniqueness is not to be underestimated. In fact, most books on control theory, when you study Lyapunov stability theory, would start by consider a dynamical system in discrete or continuous time, assume it has an equilibrium point, then let's go find a Lyapunov function. So what I'm trying to say is that Lyapunov stability theory typically starts with the assumption that an equilibrium exists. That's the usual standing setup. And without loss of generality, let's put it at the origin. I'm not going to do that at all. Here, the origin in this course will play no particular role. And instead, I'm going to talk about contractivity so that I know an equilibrium point exists and I will use X star to denote. All right. Then, if you have a map T, traditionally, the standard iteration defined by the map, so just applying T to the point, you give me an initial condition X naught, and then I apply the iteration. So that's called, sometimes it's called the Picard iteration. And now if you apply the map T, so if you generate the Picard iteration, this Picard iteration will converge to X star. So if you wish to compute X star, just apply the map repeatedly. Moreover, finally, it's quite interesting that there are multiple explicit error estimates that you can write. These error estimates, they have various names, and you can interpret them, and they can be used in different circumstances. But here, this is telling you that the distance between a time k and the final point is L to the k, which tells you the times the distance of the initial condition. Or another way to put it, if you just see how much is your first step size, so if you go from X naught to X1, this already gives you an idea of what the error will be at step K. Just know L. Or if you look at how large is your steps of time from K minus 1 to K, this also gives you an upper bound of how far you are from the final condition. So this is called geometric convergence or exponential convergence to continuous time, an a priori upper bound after just one step, or an a posteriori upper bound as you run the algorithm. So you can imagine writing a piece of the Python code and you can easily check. You just compute the distance and easily you are able to write down useful termination conditions, because you know if you want to get a certain epsilon error, well, there's the formula for you. You can find out how many steps you need to take. Now, allow me to, so in the slides, I decided to use this color that you guys cannot read to make my proofs even harder. I didn't do it on purpose. I wanted a color that would be different from the others so that we would all immediately know that this is a proof, but I now realize that for tomorrow or ever, just for this afternoon, I will change the color to something darker. I didn't think about this. So for now, let me just use this trick of enlarging. Maybe I can close that. All right, fine. Now hopefully it's readable. So I don't know that it's worth me going through every one of these proofs very carefully, but just for the record, this is a very straightforward proof. Okay, very straightforward proof. You start at time k, and you go forward h time steps. Not one, but h, where h is an arbitrary number. And now, okay, once again, the distance satisfy the triangle inequality. So if I compute the distance between x1 and x3, this is upper bounded by the distance between x1 and x2, and the distance between x2 and x3. So this is the triangle inequality. So you apply the triangle inequality repeatedly, and then so this is k plus 1. The next one up was k plus 1, k plus 2. Then you apply the Lipschitz property. You know that the distance, let me write it out, I could be more explicit here. The distance between xk plus 2 and xk plus 1 by the Lipschitz property is upper bounded by L times the distance between one step less. So this is the first term I get. And then in the second term, I use this bound here, right? I use this bound here, and I managed to remove 1 from the subscript, both subscripts, right? This is one application of the Lipschitz property of the map T, because xk plus 2 is t xk plus 1, and xk plus 1 is t xk. So I get one copy of L. And so this is the first term, is exactly itself. There's a 1. And then here is the second term, there's an L. And then if you go all the way out to time k plus h, there will be h minus 1 steps. And that's why here you get this summation. Does that make sense? Any questions? So this summation here is because I bring back every term. All right, fine. Now, this is the truncated Taylor expansion of 1 over 1 minus L. And if I instead sum it to infinity, this is going to be an upper bound. So 1 over 1 minus L, the distance from k to k plus 1. And then again, this term here, I've applied the map T L times here, starting from the initial condition. So if I go from 0 to 1, and I apply tk times, then I get to xk plus 1 and xk. And so here I have an L to the k. Right? Okay. And so I have shown to you, so I hope it was clear, but I have shown to you that, or actually I should say Stefan Banach showed to you that, right, as you look forward, you've got this bound. Now, when L goes to infinity, sorry, I forget now the limit here. I should take k goes to infinity. When k goes to infinity, the denominator is fixed and the numerator goes to 0 because L is less than 1, right? So we said that's the contraction factor, which is less than 1. So this is going to 0. And so the distance between points on these trajectories is going to 0. So you have a sequence of points, and the distance between the points is going to 0. And so now the question is, when is it true that if I give you a sequence and the interpoint distance is going to 0, does that sequence have a limit? And that's the property of the metric space being complete. So that's precisely the key point of the Banach contraction theorem. In fact, the contribution by Banach was precisely in adding the assumption of completeness in the metric space. Once you add completeness, then this tells you that the sequence must converge to a point X star. Now, this is existence. And then if you think about it, uniqueness comes from the fact that L is less than 1. If you were to have two fixed points, then you apply the map T, and the distance between the two fixed points decreases, but that's not possible. Right. So uniqueness follows from L being less than 1. I'll skip the geometric convergence. Okay, so this proof is very straightforward. It just uses the properties of a distance and the Lipschitz property of the map, and then at the right point, the completeness of the matrix space. All right, so as I have already mentioned earlier on, there is a wealth of metric spaces that appear in mathematics, but also in engineering, in the sciences, and so forth. The most simple examples arise as finite dimensional vector spaces with a norm, which basically means I have Rn, and you give me a norm, and then the distance between 2 points x and y is simply the norm of the vector x minus y. The norm could be the 2 norm, the 1 norm, the infinity norm. So this is the distance. With this distance, Rn becomes a metric space. And it is complete. It's known to be complete. In fact, even more, all norms on Rn are known to be equivalent, which we can talk about later. That's the simplest example, the most common example, and it's also very relevant in many applications. So I will essentially focus on this case. I think also because it's a simpler case, and we really want to understand it completely. Now, but there are many other metric spaces which I may not have the time to cover in these few hours. Very interesting. There are Riemannian manifolds. On a Riemannian manifold, there is a notion of an inner product at each point. So on the sphere, for example, there's a notion of inner product at each point. There's a tangent space, an inner product. You can talk about the velocity of a curve. You can talk about the speed, which is the norm of the velocity. And then you integrate the speed that gives you the length of a curve. You can talk about shortest curves between points. On a sphere, if you give me 2 points, the shortest curve connecting them is the arc of a great circle. So you take the 2 points, you take the center of the sphere, you define the unique plane that passes through these 3 points, the center of the sphere and the 2 points. They have to be distinct. If they are together, then the plane is not uniquely defined. And then when you intersect the sphere with the plane, you're going to get a circle. There will be 2 points on this circle, and there will be 2 arcs, a shorter one and a longer one, unless the 2 points are antipodal. If they're antipodal, then the plane is not uniquely defined. Still, the distance is exactly pi. So the distance is the length of the shortest curve, and it is well defined. That's the geodesic distance. And you can certainly define, study, apply Riemannian distances to define a Riemannian metric and do contraction theory on Riemannian manifolds. I'll show you some examples. People have studied this in infinite dimensional Hilbert and Banach spaces. And then also interesting, the set of positive definite matrices is a positive cone. And you can define a notion of metric on positive cones. There's an elegant work by Thomson and Birkhoff and others on something called the Thomson metric. But truly, there are many metrics. Then, depending upon the problem you're interested in, a particular metric may come into play. All right. So now, a little definition, not a definition, but just to make sure we understand each other. In these slides, and essentially also in my book, but not in the literature. When I say contractivity, I will mean to say contractivity on a finite dimensional vector space with a norm. And there's plenty to understand even just in that case. For this setup, we have available, I would argue, an essentially complete understanding in discrete time, continuous time, many examples, fully amenable to analysis. I can write the proof in a slide. Once we go to Riemannian manifolds and more complicated spaces, it's more complicated. And sometimes the search for this matrix becomes very numerical. I'm going to focus more on analytical examples that I can work out. Does that make sense? But for example, if you listen to Professor Jean-Jacques Slotin, when he talks about contractivity, for him, contractivity automatically is on a Riemannian manifold. When you talk to Rodolphe Sepulcher, maybe for him, contractivity is on a Finsler manifold with respect to something called a Finsler structure. So you need to be aware of these distinctions. All right, let's talk about norms in Rn. Let's talk about norms. So norms come in various shapes, so long as they are parameterized by a number, L1, L2, L infinity. So the norms that I am interested in. So what am I plotting here? These are the unit balls of the norms. So in other words, these sets of points here is the collection of points that is at distance 1 from the origin, right? The unit ball, the unit disk centered at the origin. If you use the standard Euclidean norm, you obtain a perfect circle, right? And in n dimensions, you get the sphere or the n-dimensional sphere. This is the diamond. And at infinity, if you use the infinity norm, then the unit ball is a box, is a cube in higher dimension, or hypercube centered at the origin. The definition of the three norms are given here for you to read. The one norm, the two norm, the infinity norm. So, okay, fine. The one norm is the sum of the absolute values. The two norm is the sum. Sorry, is the square root of the sum of the squares. And the infinity norm is the largest entry. This is called the max norm. They have all sorts of names, but I'm just going to call them L1, L2, LP, L infinity. All right, and these properties are, like as you enlarge the number, the unit ball becomes larger and larger, right? And you can define things for p less than 1, but they're not norms. But you can certainly define them. All right. So now, I forgot to have a slide here, but I am assuming that you have been exposed to the definition of induced matrix norm. So if I give you a matrix A, which lives in R n cross n, right? So a nice square object, then I can define the induced, well, and I have, so we are in Rn, and I have a norm, you give me a norm, right? Then I can define the induced norm of A by looking for the supremum value achieved over X of the norm of AX divided by the norm of X. Okay, this definition is more or less wrong. You don't want to divide by 0. If you divide by 0, you're not going to have a great career as a programmer or as a mathematician. So you take X different from 0. Or another way to do it equivalently is to ask for the supremum over all X's that have norm equal to 1. And then you just look at the norm of AX. And then you realize that the norm is a continuous function of its arguments. This is a compact set. A continuous function over a compact set achieves its maximum value. So you come back here and you just put a max instead of a sup. Does that make sense? All right. Induced matrix norm. And the induced matrix norm, well, first of all, this is an operation. I should use a different symbol, right? Some people use an I here because this norm here induces an operation on the set of matrices, right? So now this operation, let's be careful, huh? Takes an element of n times n and gives you a scalar. And now I should prove for you that this operation is a norm. I should show you that it satisfies the properties of a norm. I'm not going to do that because it's a classic standard matrix theory exercise. You've all seen this. It's kind of boring, but I should check that. All right, fine. All right. Then I hope you're all familiar with the fact that there are these induced matrix norms. And these have been studied in the past. This is the 1 and the infinity. And this is the 2 induced norm. Okay. So the 1 norm, you take the absolute value of the matrix. And by that, I mean to say the absolute value of each entry. And then you take column sums of the matrix. And then you select the maximum value you get. So the induced 1 norm of a matrix is the maximum column. I want to say sum, but I cannot say sum. It's the maximum column absolute sum. It's a bit of a weird name if you want to say it in English. Otherwise, just write the formula. And the infinity norm is the same with rows. You sum over rows. For the 2 norm, it's the largest singular value of the matrix. So you take the matrix A, you multiply with itself, A transpose A. Now that matrix is positive semi-definite because it's now symmetric, and all of the eigenvalues are going to be positive or 0. You look at the largest of them all. My lambda, I'll try to use lambda for eigenvalues. Lambda max is the largest eigenvalue, and you got to take the square root of it. Does that make sense? These are formulas that we could prove that you should have seen that are very standard, okay? Now, there is a third column to this table. I'm going to come back to this later. All right, so now, let us take Banach contraction theorem, which we have already seen, and just present it in the context of a dynamical system, even though that proof that I had in that light color was already a proof about dynamical systems. So sometimes I think to myself, the Banach contraction theorem for dynamical systems, and other times I'm thinking, it's already for dynamical system. I don't need to say it. But in any case, all right. So we are going to start by looking at a time invariant, discrete time map dynamical system described by a map F. F maps Rn into Rn, and I have a norm on Rn, and you know, I should put an I here, but I'm just going to drop it. So from the context, if the argument is a vector, it's the norm of the vector. If the argument is a matrix, the induced norm of the matrix. Okay, so we said earlier that you can define the Lipschitz constant of a map. And earlier I had written the Lipschitz constant for I had written something like I said, I had written distance Tx Ty less than equal than L distance xy. But now I am working on a vector space. So this distance is just the norm of fx minus fy, right? And if I can find a number L that makes this equality come true, that L is a Lipschitz constant. I never said that the Lipschitz constant is unique. A Lipschitz constant is any number that makes the Lipschitz inequality come true. Now, in practice, what people do, and I will also do it, is that among all of the numbers L that make this equation come true, I'll look for the smallest, and I will call that the Lipschitz constant, not a Lipschitz constant, the Lipschitz constant. I will look for the smallest number L that make this equation come true for all x's and y's in the space Rn. So this is the standard definition of the Lipschitz constant. Does not require differentiability of the vector field of the map, not the vector field, pardon me, of the map F. If your map F is differentiable, then you can calculate the Lipschitz constant of F using the Jacobian. And I hope you should remember this from your vector calculus, multivariable calculus course. And it turns out that you need to perform 3 operations in a row. First, you have to take the Jacobian of F. Then you have to take the induced norm of the Jacobian. Now you have a scalar number which depends upon x because the Jacobian depended upon x. And now finally you have to take the supremum value of the induced norm of the Jacobian, and that's going to give you a number. So here in this little formula, there are 3 steps. Jacobian, norm, supremum, and it turns out it's a little theorem which how do you prove that? Which we'll review a little bit. And these 2 definitions are equivalent. So typically you give the definition, mathematically it's more elegant to give the definition without requiring differentiability. And then you write a theorem saying, if the map is differentiable, then here's an equivalent expression, right? Fine. Now, when n is equal to 1, maybe I will use lowercase f here, maybe. Then the Lipschitz constant is just the supremum of the absolute value of the derivative of f, right? Here's the Jacobian, it's just the derivative, absolute value. When instead I am in Rn and now here things start to get interesting. What if I have a map F, which is described by a matrix A, by a square matrix A, and now it's affine. F of x is equal to ax plus a constant vector lowercase a, which will play no role in what follows, but I wanted to clarify that you can add a term here and it will play no role. So this is, I'm gonna write this f sub a to remind myself that it's really just parameterized by the matrix A. So then what happens? Well, when you apply this formula here, you realize that when you take the Jacobian, you get just a. It's independent of x, and the supremum does nothing. So the Lipschitz constant is going to be just equal to the induced norm of a, right? So now let's define a little bit of notation. Suppose that I am defining not just the 2 norm and the infinity norm, but more precisely, the weighted 2 norm and the weighted infinity norm. So I write 2 comma p or infinity comma eta. Eta will be a positive vector. Sometimes I will equivalently write infinity comma diagonal eta. Now P has to be a symmetric positive definite matrix, and eta has to be a positive vector. Maybe let me write it like this: Rn positive. Rn positive. So these are weighted 2 and infinity norms. Some people would also write this as, you would see this also as x sub p. X sub p. I have no problem with this notation. It's just that I would rather remember that there's to be a 2 there. And I suspect that I may not even be fully consistent with this notation. Anyway, I'll be careful with when I define this weighted. These weighted norms are denoted with different symbols, so but fine. So for this slide, this is the notation. So it's x transpose px to the 1/2, right? That's the weighted. So then, as we just said, the Lipschitz constant of Fa is just equal to the induced norm of A. When I have the 2 comma p or infinity comma eta, then it's just the 2 comma p or infinity comma eta induced norm, right? I did not give you formulas for the weighted induced norms, so we should do that. Keep it in mind. I'm going to skip some algebraic step. We'll come back to them later. They certainly are in the book. Now, but this slide contains one more theorem. Okay, here there's a theorem here. Well, there's 2 theorems. Here's one theorem. It turns out that the induced 2 norms with the weight p of the matrix A is upper bounded by a number L if and only if, I should prove this for you, if and only if this inequality holds. This is a linear matrix inequality. So I'm going to describe that in a second. So A transpose PA has to be upper bounded in the LMI sense, linear matrix inequality sense, by L square P. So what does it mean that I have a matrix X and it is upper bounded by Y? I mean to say that X minus Y is upper, or actually maybe let's do it the other way, that Y minus X is greater than or equal to 0. So if x and y are symmetric, their difference is symmetric. So this greater than or equal to 0 means the symmetric matrix is positive semi-definite. So right now in this slide, I am assuming that you are familiar with positive semi-definite and positive definite matrices. So if you're not, then please study them up during the break later. All right, so the calculation of the Lipschitz constant with respect to a quadratic norm, an L2 norm, a weighted L2 norm is known to be equivalent to the solution of an LMI. Well, that's not exactly right. Here I'm not calculating the 2 norm. I am giving an upper bound on the 2 norm. It's the same as verifying that an LMI satisfies. To compute the 2 norm, either I use the formula with the singular values, or I need to run a bisection algorithm where I give you an L and I see if this LMI is satisfied. If it's satisfied, I can make L smaller. Now, it turns out that there's a similar result that holds for the non-Euclidean infinity norm. And this result says that if you want to see that your induced infinity norm weighted is bounded, then what you can do is you can verify that this linear inequality, these are now vectors on the left and the right hand side. These are not matrices like before. That this linear inequality is satisfied. You take the absolute value of the matrix A. You remember I said it's the absolute value of each entry. Eta transpose upper bounded by L eta transpose. Upper bounded here means entry-wise. Each entry is upper bounded. The upshot of these two equivalences is that checking a certain L2 gain requires solving an LMI. Checking an infinity norm gain requires solving linear inequalities. So it doesn't require you having a PhD in numerical analysis to know that linear inequalities are much faster to check rather than LMIs, much faster. All right. And now comes your Banach contraction theorem written for a vector space with a norm. Suppose that I have a, I'm changing notation a little bit here. I have a map F and it has a Lipschitz constant, let's call it rho, and rho is less than 1. Then I will call the map F contracting, or maybe I'll call it, sometimes I call it strongly contracting. Sometimes I will call it rho strongly contracting. Rho strongly contracting. What does that mean? That means that if you take any two trajectories, determine, so this is x0, this is x1, this is x2, and so forth. That's y0, this is y1, that's y2, and so forth, right? If you look at these trajectories, the distance between them is diminishing as you go forward in time, in discrete time. Here, I am plotting, hopefully you can see it, I am plotting unit disks in the infinity norm centered up the x trajectory. Actually, I misspoke, not unit disks. I'm plotting decreasing disks of the exponentially decreasing or geometrically decreasing size centered at x0. And as I draw this cube centered at x0, if I draw them shrinking at the right rate, the rate rho, then the trajectory y is guaranteed to be in those boxes. So y0 is in the first box, therefore y1, y2, yk is in the kth box centered at xk with the radius, which will be rho to the k times the initial radius. So now this is saying that the two trajectories are given any two initial conditions, the two trajectories are converging to one another at the geometric rate. I don't know why, I think it's historical. If in discrete time, people talk about geometric rate, and that's the same as exponential rate in continuous time. But the Banach contraction theorem tells you more. The Banach contraction theorem, let me animate it for you, tells you that there must exist a point here, x star, to which both x and y trajectory converge. Actually, to which any other trajectory converges to. So in other words, if I take any other randomly selected initial conditions, maybe there will be some oscillations or something, but they are going, all of them, all trajectories are all converging to the unique geometrically stable point x star. So in brown here, I've illustrated the theorem. Does that make sense? And I don't have to prove anything here because this theorem about discrete time dynamical systems on a vector space is exactly the Banach contraction theorem. It's really just an like special case because it's for a vector space rather than a metric space. Okay, any questions? All right. I think that it has been 1 hour, and therefore I will take a 4-minute break. Sorry? Make it 5. 5. And I stopped. I'm going to stop recording. All right, welcome back. We took a little break. So we just saw the discrete time. So the standard Banach contraction theorem, which one could also say the Banach contraction theorem for discrete time dynamics. But now I would like to give you the Banach contraction theorem for continuous time dynamics. So for a vector field that describes a differential equation, right? And so it turns out that I need to introduce a new algebraic operation called logarithmic norm. Now, the logarithmic norm is not a norm, so the name is not the most satisfactory, but nevertheless, it is. If you look at this formula, it looks like a derivative of the norm, and you can give it that interpretation. It is again an operation that this mu function takes a matrix, a square matrix, and gives you a number. So it is, you give me a matrix, I compute its logarithmic norm. It is not a norm. It does not need to be positive. It can be negative. In fact, it will be very useful for us when it is negative. And you may argue, well, Francesco, now this is a typical definition. I'm not even sure it's well posed. And I would argue, don't worry about it, just like you did not worry too much about the definition of the induced norm. You just have formulas for it, right? Let me just quickly mention. In this table, for the 1, 2, and infinity norm, there are formulas for the induced matrix norms, and there are formula for the induced logarithmic norms. So it's the same level of complexity. You may be less familiar with it, but it is the same level of complexity. You're still taking row sums, column sums and row sums, respectively, for the 1 and infinity norm. But here you're taking absolute values only of the off-diagonal terms. So this formula here looks much more, this formula here looks much more complicated. One more time. This formula here looks much more complicated than the one on the left, but it's really the same. The only change is that the diagonal entry AJJ is not can have negative value. You don't take the absolute value of the diagonal entries when you are taking these column sums. And the same is true for the infinity norm. And for the 2 norm, this was the largest singular value of the A matrix. And now instead, you do not take products of matrix A. You take the sum of A with A transpose. You divide by 2, which now means you are considering the symmetric part of A. The symmetric part of A, it's a symmetric matrix, right? And clearly it has only real eigenvalues. And then you consider the largest eigenvalue, lambda max, of the symmetric part of A, right? I think you're all familiar with the concept that if you have a matrix A, you can always write it as A plus A transpose plus A minus A transpose divided by 2. This first part is the symmetric part of A, and that's the skew symmetric part of A, right? So in the calculation of the log norm of A with respect to the 2 norm, you use only the symmetric part. The skew symmetric is forgotten. All right, so please don't worry too much about the log norm. This is just a norm. Now, there is a beautiful reason why induced norm and induced log norms are like twins, are related to each other. As you know, the induced matrix norm is always, so here, what am I plotting? What am I plotting here? You give me a matrix A, and I write spec A to denote the set of eigenvalue, the spectrum of the matrix A. I let lambda be an arbitrary eigenvalue, and I plot each eigenvalue as an X here in blue, right? So this matrix is what is it? A 6 by 6, a 6-dimensional matrix, right? Question. Yeah, I'm recording. Thank you. Thank you. Thank you. Thank you. For a second, my life flew in front of me. No, I'm recording. These X's are the eigenvalues of the matrix A. And now you can draw two circles. You can draw the circle, which is both of them centered at the origin. The smallest circle that includes all of the eigenvalues is called the spectral disk. And its radius, it's called the spectral radius. So this rho of A is the spectral radius of the matrix A. And it is known that the spectral radius is lower bounded by any norm. Every time you take the norm of A, you cannot get a number smaller than the spectrum. Does that make sense? The spectral radius is a lower bound on each norm. And the stability of the linear system is usually determined by the spectral radius. In the contraction mapping theorem, you're using norms. The norms is an upper bound of rho A. So when rho is less than 1, it may be that the induced norm of A is greater than 1. So now, if you are trying to apply the contraction theorem, then you are in trouble because you would like that to be less than 1, and rho is less than 1, so you know it's converging somehow from your linear systems theory. Now, the reason there is a gap here between spectral radius and induced norm is because the norm that I am using is not efficient. This gap here is an efficiency gap. I am using the wrong norm. I'm far away from rho A. And there is going to be a section in chapter 2 of the lecture notes of the book, which talks about choosing optimal norms so that this gap becomes 0 in some cases, arbitrarily small in other cases. If the dominant eigenvalues or the eigenvalues which are on the unit, which are on the spectral radius are isolated, have multiplicity 1, then you can make this efficiency gap go to 0. You can design an optimal norm. So I'm calling a norm optimal or efficient depending upon how close it is to the spectral radius. Because once again, the bound that you should remember is that it is always true that rho of A is less than equal than the induced norm of A for every norm. For every norm. And if the norm is optimal, you're matching it. Now, this is the picture for discrete time dynamical systems, where the spectral radius plays a key role. Now, for continuous time dynamical systems, there is a slightly different picture. These are the same eigenvalues that I have plotted. It is still the spectrum, the collection of eigenvalues of A. Now, in continuous time dynamical system, for continuous time linear system, you know that stability is determined by the spectral abscissa. The spectral abscissa is the largest real part, not the largest modulus. In discrete time, it's the largest modulus of the complex number, right? In continuous time, it's the largest abscissa. So here, I have drawn this vertical line, center or passing through the eigenvalue with the largest real part, and the spectral abscissa is I will denote by the symbol alpha of A. The log norm of A is always an upper bound on the spectral abscissa. So alpha of A is a lower bound on mu of A. And again, if I choose the optimal norm, I will manage to decrease this gap arbitrarily. So this is an efficiency gap. Maybe I will call it a logarithmic efficiency gap because this is the logarithmic norm if I want to make sure I distinguish between the two. And then I can talk about log efficient or log optimal. And again, if this eigenvalue is as multiplicity 1, then I can find an optimal norm. If it has multiplicity, repeated multiplicity, then I cannot find it optimal, but I can, you give me any epsilon and I can get close to it. All right, so literally, in the two pictures, the induced norm plays with respect to the spectral radius the same role that the log norm plays with respect to the spectral system. Both of them satisfy, here I have only written these properties only for, I have the properties later on, but both of them are convex functions. Let me just point. Both the map that goes from A to the induced norm of A or from A to the log norm of A, both of these maps are from the set of matrices to the scalar. They're both convex in the argument. Both of them are convex. Notice the spectral radius and the spectral abscissa are not convex functions of the entries of the matrix A, but the induced norm and the induced log norm are convex functions. All right. And the convexity comes from subadditivity and positive scaling. So these are the two subadditivity means the arguments, you get upper bounded by the, and the scaling is when you can bring a positive scaling or positive homogeneity when you can bring a positive number out. All right. So now, why did I introduce this new operation called the logarithmic norm? Well, that's because I wish to tell you about the Banach contraction theorem for continuous time dynamical system, because the one for discrete is clear. So now the map F denotes a vector field I'm thinking about. And again, I have a norm on Rn, and now I have the log norm, mu. To be honest, I don't love the symbol mu for the log norm. This goes all the way back to the PhD thesis by Dahlquist. I don't think it's a great symbol. I wish it was looking like the induced norm, but fine. Now, earlier we defined the Lipschitz constants in two ways. A way that, let me call it the integral way, where I don't take the Jacobian, and then another way where I take the Jacobian, right? Let me talk about the second way first, the second definition. So suppose the F is differentiable, then I'm going to define a new constant, a new operation, which is called the one-sided Lipschitz constant, or some people would call that the logarithmic Lipschitz constant. In fact, I showed you a slide where there were 11 different names for this same thing. But I'll stick with the language that Dahlquist used in 1976, and he used the word one-sided Lipschitz constant. And to compute the one-sided Lipschitz constant, so I put an osLip there, you need to perform three operations just like before. You have to first take the Jacobian, you now have a matrix. Then you take the induced log norm. Earlier you were taking the induced norm. And then you take the supremum over X. Does that make sense? It's just the same as before, but instead of using the induced norm, you have to use the induced log norm. Now, if you have a scalar map, then the one-sided Lipschitz constant turns out to be, well, just the log norm when you are in R, not Rn, then any norm becomes just the absolute value. Then the log norm is just the arguments. It simplifies to be the log norm of a scalar number, lowercase a, is just a. And so the point is that the one-sided Lipschitz constant of a scalar map from R to R is just the largest value of the derivative of f, not the absolute value of the derivative, just the derivative. That's why it's also called one-sided Lipschitz, because you're only upper bounding f prime, not upper and lower bounding f prime. Another way, equivalence, well, actually, this particular way in gray works also when the map F is non-differentiable. But okay, suppose it's differentiable, so it's an equivalent way. Another equivalent way is, now I need to write a formula. I need to write, let me write it for in a way that it's easy. So I need to look for a number B such that f of x minus f of y transpose x minus y is less than equal than 0, or, well, is less than equal than b times x minus y squared. So when I am using the 2 norm, b is a one-sided Lipschitz constant for f, if this equation holds for all x's and y's. And just like before, I am going to be looking at the smallest value of b such that these equations hold. And when I do that, that is the one-sided Lipschitz constant of f with respect to the 2 norm. Does that make sense? Maybe I should write this a little bit better. Right now, I sort of improvised and it looks like slightly unclear. All right. Okay. So if you have, I don't know if you guys at the back can see, I hope you can. With respect to the standard 2 norm, the one-sided Lipschitz constant is the smallest number b that gives you this upper bound for every x and y. So this upper bound is the inner product, right? It's the dot product fx minus fy into x minus y. Does that make sense? Now, sometimes I will denote an inner product by, people sometimes use like a single bracket or a double bracket, f of x minus f of y into x minus y less than equal than and the same as before. Does that make sense? So it's a bit of a, now this needs to grow on you. It's a bit of a surprising thing. I have to take an inner product f of x minus f of y into x minus y. Now, why am I using some weird square brackets? Why am I doing that? Because you see, not all norms arise from an inner product. One norm, the infinity norm, polynomial and polyhedral norms, composite norms, and other norms that one may define do not arise from an inner product. So here in blue at the bottom, I have given to you the formula with an inner product. But now this formula only works when I have an inner product. What if I don't have an inner product? How do I generalize that? And so to generalize that, I am going to define for you what is the correct operation to put there on the left-hand side. Does that make sense? But the intuition is the same. The intuition for the inner product case is the correct one. It is f of x minus y into x minus y, where you need to understand what is that correct operation. And just like in the discrete time case, the first definition works when f is not differentiable. The second definition works when f is differentiable. Actually, to be even more specific, if f is locally Lipschitz, which means that f is differentiable almost everywhere by Rademacher's theorem, then there's another thing you can do. You can say the essential supremum of mu of d f of x, where x is everywhere the map is differentiable. So if it's differentiable, it's this formula. If it's locally Lipschitz differentiable almost everywhere, you can still use the log norm of the Jacobian almost everywhere, wherever it's the derivative is defined, the Jacobian is defined. If it's not even locally Lipschitz, then you can use the first formula, which is you don't have to take any derivatives at all. Now, I have defined this log norm, and then I have defined one-sided Lipschitz constant. Why did I do that? Well, actually, sorry, before I tell you why I did that, let me show you another example. So just like before, first we saw the scalar case. The one-sided Lipschitz constant is the upper bound. Now let us look at the affine map case, just like before, right? All right, so here I need to take the Jacobian of f sub a, but f is linear, well, affine, so the constant term goes away. And so whenever I have one-sided Lipschitz constant of fa, this is going to be equal to just the log norm of a. Because I take the Jacobian. Once I take the Jacobian of fa, I get a, and then I at the end I will take the supremum, but a does not depend upon x anymore, so the supremum goes away. It's just a log norm, right? Okay, so for an affine map, I just have to take the one-sided Lipschitz constant of the matrix. Perfect. Okay, so then just like we did before, this is fully reasonable and understandable. That no, my mistake. Sorry, let me do it again. Up until here, this is fully reasonable, right? One-sided Lipschitz constant of fa is equal to the log norm of a. If I use the 2p norm or the infinity eta norm, that's the 2p or infinity norm, the infinity eta log norm, right? This is what I've said so far. But now in this slide, there is another theorem. What does this additional theorem says? This theorem says that this is a theorem about log norms. So this is not a theorem about nonlinear dynamical systems or even contraction theory. This is just a theorem about linear algebra and matrix theory. And the theorem says that the log norm of a matrix A with respect to a weighted 2 norm with a positive definite matrix P is upper bounded by a constant L if and only if a certain linear matrix inequality LMI is satisfied. And what is this LMI? This is A transpose P plus AP upper bounded by 2LP. Does that make sense? Again, this is in the positive definite sense. Are you okay with this? Are you guys familiar with this LMI? This LMI, well, actually, maybe now I can take a second and draw some connection with other concepts. So earlier in the discrete time case, the LMI was A transpose PA less than equal than LP. And now, so this was the discrete time case, discrete time. This is continuous time. So now, actually, so this is related, and that's related to the discrete time and continuous time stability LMIs. So when you study linear system theory, you will see that there is a theorem, for example, that says that A is Hurwitz, which is to say all of the eigenvalues of A have strictly negative real part, if and only if there exists a positive definite matrix P such that A transpose P plus PA is negative definite, right? That's the Lyapunov LMI characterization of stability in continuous time, right? And A is sure stable. So this is Hurwitz stable in continuous time. A is sure stable in discrete time, which means all of the eigenvalues have modulus strictly less than 1, if and only if there exists a positive definite matrix P such that A transpose PA is strictly less than P. So this is the discrete time stability LMI, and this is the continuous time stability LMI. Now, when L here is less than 0, and or in the discrete time here L maybe is less than 1. So I would say this LMI. So let's only talk for a second about the continuous time one. Otherwise, I'm going to confuse you. So when L is negative, this LMI is implied and implies this one. So if this is strictly less than 0, there exists a number L negative that makes the other one whole, right? And then if that holds, clearly this holds with L negative, clearly this holds. So the difference between the stability LMI and what I would like to call the contractivity LMI is that the contractivity LMI has the explicit contraction rate L in it. If L is negative, the absolute value of L is the contraction rate. Whereas the stability LMI does not tell you where the spectral abscissa is. And this is true both in continuous and in discrete time. Again, what I'm trying to say here, I'm sorry, maybe my slides are not optimal right now, is that equation star and equation double star, equation star with L less than 1, and equation double star are equivalent. Well, in the sense that if double star holds, then there exists an L less than 1, which makes equation star hold. And if equation star holds, clearly equation double star holds as well, without any qualifier. And the difference is that this is only telling you it's sure stable, whereas the one up there is telling you the contraction factor is L or smaller. Any questions? Okay, so this theory of Lipschitz constant and one-sided Lipschitz constant is closely connected to the theory of LMI, characterization of stability in discrete time and continuous time. But it is closely connected when the norm that you use is the 2 norm. If you're using the 1 norm, the infinity norm, or other norms, then it's a generalization of it, right? Because now it still works. Now I'm ready to tell you the continuous time Banach contraction theorem. What does that mean? Suppose I have a map F, and suppose the one-sided Lipschitz constant is strictly negative. And let's suppose it's equal to minus C, where C is positive. So there's a minus sign here that it's a bit annoying, but just to remember, this is unavoidable. If you have a continuous time system, the eigenvalues have to have negative real part, and then the rate at which you converge is the absolute value of the largest eigenvalue, right? Now, this is the same picture as before. I have 2 trajectories, X and Y. I draw a ball in the infinity norm centered at the X trajectory. I pick another initial condition, Y naught, in the same, in the unit ball of X naught. And then as time progresses, I draw smaller balls according to the rate e to the minus ct. So here this was the unit ball, and then I write each ball, I write with radius e to the minus ct. And the y trajectory has to belong in that ball, and that ball is shrinking exponentially fast. And that's the first statement. And then the second statement, just like before, the Banach contraction tells you that there does exist a point x star, and not only do the x and y trajectory converge to it, but really every trajectory from everywhere in space will converge to it exponentially fast with rate c. Okay, so this is the Banach contraction theorem in continuous time over a vector space. The condition is the one-sided Lipschitz constant being negative. If I were to be on a solid cone and I have an ordinary differential equation over a positive definite matrices, right now, I don't even know what the condition looks like. I know the condition in discrete time, but not in continuous. Now, I'm gonna use a couple more minutes to come back here and tell you the story about this light gray formula. Why is my formula in light gray? It's in light gray because I have an undefined operation, right? I did not tell you what is this operation when the norm is not an inner product norm. What is that operation when I have the infinity norm, for example, or the 1 norm? So let me remind you of some properties that hold for the inner product, and then I'll generalize them to norms that are not dependent upon, that do not arise from an inner product. So if I take 1/2 x transpose function of time, x of time, and then I take the derivative with respect to time. What do I obtain? Well, then the Pareto formula, you will obtain x dot transpose of time, x of time. Any questions? That's obvious, right? You multiply the first one by the other, 1/2. All right. Also, it turns out that this quantity depends if x. Well, I should have said that the curve is differentiable, right? Otherwise, I cannot take the derivative. So for it, you give me a curve in x function of time. If it's differentiable, this quantity is differentiable. X transpose x is differentiable. And so I take the derivative with respect to time. Maybe I put the 1/2 there because I want to make sure that I don't have the, and then I get x dot into x. Now, let me generalize it. Sometimes for some norms, even if the curve is differentiable, the norm of the curve might not be differentiable. For example, if you have the infinity norm, so it's the largest value between x1 of t and x2 of t. Let's say it's in R2, I have a vector with two entries, x1 and x2, and the infinity norm is the largest between the absolute value of x1 and the absolute value of x2. But then imagine I have x1, x2, I plot them as a function of time. They could be changing the order. One can become smaller, the other becomes larger. At the instant of time when the two entries are equal and then they change the order, the infinity norm of that curve is not going to be differentiable because the derivative was diminishing and now it increases. So then there is a generalized derivative called the upper right Dini derivative, which you need to use when you have a more general norm. That's pretty much all I'm going to say about it, because this generalized derivative it's a very simple, very friendly concept. Is basically just a time derivative. It's still there will be unique points in time when it's not defined, but it doesn't matter for the purpose of what follows. All right. I would like to give a name to this formula, this super easy formula that you don't even usually worry about because it's so easy that you just use it all the time without giving it a name. But I want to generalize it. So just let me give it a name. I would like to call this the curve norm derivative formula because I need to have a curve. I take the norm of the curve and then I take the derivative of it. So 3 operations, as sometimes it happens to be the case. Does that make sense? So this is the key formula that I need to generalize. How do I generalize that? Now, before I continue, really the inner product has many other properties. For example, here's another remarkable thing, which is true. That the 2 log norm of the matrix A, which this equal sign is the formula that I've given to you 3 slides ago. It's the largest eigenvalue of the symmetric part of A. It turns out that it's equal to the largest value taken by AX into X when X is a point is an arbitrary vector with unit norm. And this I could write a max instead of a sum. So to the left of the sign here, this is the log norm, and to the right is something defined by the inner product. So it's a formula that puts together the 2 log norm and the largest value taken by the inner product. So it's an interesting thing. It still happens to be true. Now, an inner product has many properties. For example, this is a subset of the properties. It's additive. So in the first argument, it's homogeneous. You can bring a positive and any number out. It's positive definite, and it satisfies the Cauchy-Schwarz inequality. And also the inner product is compatible with the norm that it defines. So in other words, that's the way you define the norm. Okay, so in the next slide, I am going to, just to prepare you, the next slide is going to be identical to this, except that there will not be an inner product. There will be a generalized operation which will work for arbitrary norms, which are not the Euclidean norm, the two norm. Does that make sense? For lack of a better term, I'm going to call these new operations, I will call it a weak pairing. And the word weak is because it has the minimal number of properties required to make the theory works. In the analysis literature, there are other pairings, and this one has weaker property than those. Okay, so that's why I'm using the word weak. But don't worry too much about it. I'm just going to call it pairing for everything that matters. So I need to define an operation that makes this equation come true. You give me any norm, you give me any differentiable curve x of t, and I would like it to be true that when I take the time derivative, maybe I divide by 2, so I get rid of the square, right? Of the square of the norm, I obtain something that has x dot into x, just like before. Before there was the inner product. Does that make sense? Any questions? So what is that operation? And moreover, it will magically, it's not magical. I mean, there are, if you really start to think about the linear algebra behind this, it's going to make sense. It will also happens to be the case that there will be another identity that will always hold, and that will have on the left-hand side the log norm, and on the right-hand side this pairing, and it will be a supremum or a max over all the vector x with union norm of ax into x, just like before. Actually, if I go back, I think this is called the Courant-Fisher theorem. Tells you that if you have if this is the Courant-Fisher theorem telling you that lambda max of a symmetric matrix X is equal to the maximum value over norm of X equal to 1 of X transpose Sx. So this one is a standard identity in matrix theory, telling you that if you want to extract the largest eigenvalue, you just maximize overall the vector X on, essentially this is the unit sphere, and you get them out like this. So this is also called the numerical range, but fine. And so here I wrote S and S because up here I had A and I had to take the symmetric part of A, right? Fine. So this is called the Courant-Fisher theorem, and the generalization, people call that the Lumer equality, okay? Now, there are two ways to understand these pairings. One way is to say, I want the pairing to satisfy the curve norm derivative formula. What is it? Another way is an axiomatic way, and they're equivalent, of course, right? And the axiomatic way is to say, okay, a weak pairing is going to be an operation. You give me two vectors, it gives me a number, and it has to satisfy these properties, okay? And now I made this too small, so you cannot read. What are the properties? It has to be subadditive in the first argument. It has to be positive homogeneous if I multiply by a positive number b. It has to come out. And another good property. It has to have positive definite. When I multiply x into itself, it has to be positive, just like before. And it has to satisfy Cauchy-Schwarz, just like the inner product. Does that make sense? The two methods are equivalent. You either ask for the curve derivative formula or for the pairing, the axiomatic, and it's all going to work out. So now you could tell me, Francesco, you define these weird abstract operations, the log norm. Well, the log norm was just like the induced norm, and you were comfortable with that, so it's not a big difference. And now these pairings, this seems to be very abstract, but let's make that concrete. Let's look at what they are, right? Let's just look at the formula. So I am going to give you three formulas. First, let's do let's do the two norm, and then we'll do the one and the infinity. The two norm, the pairing is just the inner product, okay? So if here I did it for the weighted case. If you have a positive definite matrix P as the weight inside, then the pairing is just the inner product where you stick a positive definite matrix P in the middle, X transpose PX. Does that make sense? So X transpose PX is a weighted inner product. The surprising formulas are the ones for the one an infinity norm. For the one norm, the pairing is you take the second argument and you take the one norm with the second argument. You take the sign operation of y. The sign is computed entry-wise. So if you give me a vector y, I take +1, -1, or 0, depending upon whether the number is positive, negative, or 0. Just a sign operation, entry-wise. And then I do the dot product with the sign of y and x. Right. So it still is looking like the old inner product because I have yi, the sign of yi multiplies xi, summed over I, but it's really the sign, not yi. And then I sum all of the entries, the absolute value of all of the entries of y. So it's really not, it's really different, right? From an inner product. And now the infinity pairing works like this. It's just xi, yi. So remember, the inner product would be the sum of yi, xi. Here you take the largest of xi, yi. So you take all the dot product, all the scalar products, xi, yi, you look at the largest. However, there is a twist which makes things a tiny bit more complicated. And it goes like this. You do not look at the maximum value of this over all indices. You only look at the indices at which yi takes its maximum value. So here, maybe I should change. Just allow me a second here. Let me make it easier to read. So, oops. So if only the indices at which yi, the absolute value of yi is equal to the infinity norm of yi. So basically only for the indices yi, where the vector y takes its maximum value, you maximize over that. Now, these two formulas, x star and x double star, I will in practice never use. I'm not going to use them very much in applications, but they're well defined, properties are clear, and I will use the pairings as a way of doing proofs, and typically to check contractivity I will use log norms. So let me go back to explain again to you. There are two equivalent definitions of the one-sided Lipschitz constant, one with the pairings and one with the log norm of the Jacobian. So typically it's easier to use the second in examples. And so the formulas for the weak pairings that I just showed to you, you don't end up using them all that much. In some application, maybe you do. And if you do, that would be great. But more often than not, people use just a log. But they're equivalent, I mean, unless the map is non-differential. All right, so this concludes, allow me just one more second. Yes, this concludes the lecture. When we come back, I will continue the story and give you some additional information. So thank you all. I'll see you at 3:15.